24.1 billion kilometers from Earth, a machine the size of a small car is flying through almost complete darkness at nearly 61,000 kilometers per hour. It has no fuel to slow down. It has no way to turn back. And right now, as you are watching this video, Voyager 1 is still listening. It is listening to something no other human-made spacecraft has ever been close enough to measure in quite the same way. A sound so faint and so incredibly subtle that years of data sat inside an archive before a researcher noticed what was hiding between the dramatic events. A faint, steady hum. Not a sound coming from the spacecraft. Not a transmission from another civilization. Not something mysterious moving through the darkness. It is the signature of the space between the stars. And once you understand what that hum actually represents, where Voyager 1 is today, what it costs to keep the spacecraft alive, and what engineers are doing in August 2026 to extend its remaining scientific life, you begin to understand why this may be one of the most remarkable engineering stories of our time. Voyager 1 launched on September 5, 1977. That was almost half a century ago. It was never designed to survive this long. Its original mission was essentially a planetary tour. Jupiter. Saturn. A handful of observations. Then, eventually, silence. The spacecraft, its systems, its software, and even its nuclear power sources were designed around a mission that was expected to last only a few years. Nobody designing Voyager in the early 1970s seriously expected engineers decades later to still be sending commands to it from Earth. But here we are. Nearly 49 years after launch, Voyager 1 is still flying. Its signal is still reaching Earth. And engineers are still fighting to keep its remaining instruments alive. To understand why that matters, you have to understand where Voyager 1 is. The number alone is staggering, tens of billions of kilometers from Earth. But the real story is what surrounds it. Our sun is constantly breathing. It releases a stream of charged particles known as the solar wind. This flowing plasma expands outward through the solar system, carrying energy and magnetic fields with it. For billions of kilometers, the solar wind dominates the environment around the sun. But eventually, it encounters material coming from beyond our solar system. That interaction creates a vast invisible region called the Heliosphere. And at the outer boundary of that region is the Heliopause, where the solar wind finally gives way to the interstellar medium. Beyond that boundary is a completely different environment. The interstellar medium is an incredibly thin mixture of gas, plasma, dust, magnetic fields, and energetic particles spread throughout the space between stars. It is extraordinarily empty. The air inside a single cubic centimeter around you contains an enormous number of molecules. The region Voyager 1 is traveling through contains far fewer particles. But almost empty does not mean completely empty. And that distinction is crucial. Voyager 1 carries an instrument called the plasma wave subsystem. Its antennas can detect extremely weak electrical oscillations produced by charged particles surrounding the spacecraft. Scientists can translate those measurements into frequencies that humans can hear. And when those frequencies are shifted into the audible range, something extraordinary emerges. A faint, haunting hiss. For years after Voyager entered interstellar space, scientists mostly noticed the dramatic signals. Occasionally, an enormous eruption from the sun would send a shock wave racing outward. When one of those shocks eventually reached Voyager, it disturbed the interstellar plasma and caused it to oscillate. The spacecraft would detect the event. The data would become much stronger. And then the disturbance would fade. For a long time, the quiet periods between these events were treated as essentially uninteresting. But the quiet was not empty. There was something there. Something much weaker. something continuous. In 2017, a graduate researcher examining Voyager's plasma wave data looked closely at the portions of the recordings that had previously seemed like background noise. Instead of focusing only on the spectacular solar events, she examined the quieter data between them. And there it was. A narrow, extremely weak signal. A persistent monotone hum. It wasn't a sudden burst. It wasn't a solar flare. It wasn't a spacecraft malfunction. It was a continuous signature of the plasma surrounding Voyager. The discovery revealed something important. The interstellar medium was not perfectly smooth. It had structure. It contained small-scale variations, turbulence, density changes, and subtle fluctuations. In other words, the space between the stars had texture. And Voyager 1 had been recording that texture for years. The spacecraft had been listening to the interstellar medium long before anyone realized how much information was hidden inside the quiet portions of its data. That is what makes Voyager's discovery so remarkable. The spacecraft did not find an alien message. It did not discover an artificial signal. It found something more fundamental. It detected the environment between the stars itself. The faint voice of interstellar space. And today, that voice is still reaching Earth. But keeping Voyager alive has become increasingly difficult. The plasma wave subsystem is now one of only a small number of scientific systems still operating aboard Voyager 1. Other instruments have been switched off because the spacecraft simply does not have enough power to operate everything anymore. Voyager's power comes from radioisotope thermoelectric generators, or RTGs. They have been producing electricity continuously since launch. But radioactive material decays. The available power slowly decreases. Voyager loses several watts of generating capacity every year. That may sound insignificant. It isn't. After nearly 5 decades, the spacecraft is operating with only a fraction of the electrical power it had when it left Earth. Every watt now matters. Engineers have been forced to make painful decisions. One instrument goes dark. Then another. Systems are carefully shut down. Heaters and other power-consuming components have to be managed. The goal is simple: keep the spacecraft warm. Keep the computers functioning. Keep the transmitter operating. Keep the antenna pointed toward Earth. And, above all, keep at least some scientific instruments alive. Voyager has already survived failures that would have ended almost any modern spacecraft. One of the most remarkable examples came in 2023, when Voyager 1 began transmitting a stream of corrupted data. The spacecraft was still receiving commands. Its transmitter was still functioning. Its antenna was still pointed toward Earth. But the data coming back could no longer be interpreted correctly. The problem was eventually traced to the spacecraft's flight data system. A portion of its memory had become corrupted. For a spacecraft built in the 1970s and operating billions of kilometers away, this was an extraordinary challenge. Engineers could not simply replace the computer. They could not physically access the spacecraft. They had to diagnose the problem from Earth and develop a software solution that could be transmitted across interstellar space. The team eventually discovered that part of the damaged software could be relocated into unused memory. But even that required rewriting references and reorganizing the code. To make room, engineers had to remove old software associated with Voyager's long-finished planetary encounters. Code written decades earlier for a flyby that had been over for generations was sacrificed to save the spacecraft's ability to communicate. The recovery worked. Voyager began sending understandable data again. It was another reminder that this spacecraft is not simply a machine. It is a time capsule of engineering. Its computers were designed before the modern internet existed. Its software was written before most of today's engineers were born. And yet it is still operating in interstellar space. But every year makes the situation more difficult. In 2025, NASA shut down Voyager 1's cosmic ray subsystem to conserve power. In 2026, another scientific instrument, the Low-Energy Charged Particles instrument, was also switched off. Every shutdown represents a permanent reduction in what scientists can learn from this unique spacecraft. Because once an instrument is turned off, there is no guarantee it can ever return. And that is where the latest engineering effort becomes especially important. The team has been developing a complicated power management strategy internally nicknamed the Big Bang. The goal is to reorganize how power is distributed across the spacecraft, replacing or bypassing higher power operations with lower power alternatives wherever possible.